Hello, this is Mr. Craig, and this is quiz number 2 for period number 3. Let's go ahead and get started here. Questions 1 through 4. The set of letter choices below is a list of elements. Actually, it's a list of compounds and elements. Select one letter choice that best fits each statement. A choice may be used once, more than once, or not at all. Number 1 says this molecule contains double bonds and a linear geometry. Hopefully, by doing these quizzes here, you figured out that carbon dioxide is our only choice here. In other words, it makes a double bond on that carbon, no lone pairs. Therefore, it has a molecular geometry that's linear, and it also has a bond angle of 180 degrees. If you were asked to determine the hybrid orbitals for something like this, it would be sp hybrid orbitals, because we have 2 external atoms. Our potential for this is 2. Hopefully we have some more opportunities to talk about hybridization here, but make sure that you can do that. Alright, so number 1 obviously is number 2. Or I'm sorry, letter A. Number 2, it says the molecule has triangular planar geometry, or trigonal planar geometry. That's probably the better way to say it. Well, we already know that carbon dioxide is linear. Boron, don't forget about boron. Boron is the moron. So when we look at the periodic table, boron's in group 3 here. Boron is very exceptional because it's not quite a full-blown non-metal here, but it does fit the criteria of a non-metal because it's right along that stair step right here. Okay, so technically speaking, boron is a non-metal, but since it's in group 3A with all these other non-metals, it is behaving like a non-metal, but it is very unique in that the fact that it only wants to have 6 valence electrons total. So when we draw boron and we put fluorines on there, remember fluorine does not want to have a double bond, so do not go ahead and put a double bond on there. This is actually the structure for this. Now, for the sake of time, unless the question asks you to draw the Lewis structure, I wouldn't include those other dots. But the trigonal planar geometry here is boron trifluoride. Sorry. Ammonia actually has a lone pair of electrons, so there's no way that actually forms a trigonal pyramidal shape if you're looking only at the atoms, but it forms a tetrahedral with that lone pair of electrons. Nitrogen, although it is only 2 atoms, forms a linear shape. 2 points form a straight line. And carbon tetrachloride, CCl4, okay, it's going to be tetrahedral as well because, again, carbon always wants to have 4 bonds. Alright, so number 2 should be letter B. Number 3 is soluble in water. What we're looking for is a polar compound. Carbon dioxide is nonpolar. BF3 is nonpolar based on the shape that I just had drawn over here. Nitrogen was nonpolar. Carbon tetrachloride is nonpolar. Our only polar compound is ammonia. Now, when we talk about being soluble in something like water, water is a polar compound. How do we know water is a polar compound? Well, because if we draw the Lewis structure for this thing, it forms a bent shape. Now, it may appear to be a linear shape, but don't forget these lone pairs of electrons here do have an influence. And so when we look at the oxygen, it'll have a lone pair of electrons on top. One of those pairs will be lone, and then the 2 hydrogens. So we actually have this bent shape. So the lone pairs of electrons don't have any influence on the push or pull, so we actually have a polar molecule. In other words, if we're looking at dipole moments, drawing these, actually the oxygen would have the greater attraction for those shared electrons. So again, it's a polar compound. The big saying here is like dissolves like. In other words, polar compounds dissolve other polar compounds. Non-polar compounds dissolve non-polar compounds. Now, how are you going to know the difference between a polar compound and a non-polar compound? Polar and a non-polar compound. You should be drawing these Lewis structures out. Alright. Number 4, this molecule is a weak base. It seems like I've been saying ammonia, ammonia, ammonia. Hopefully everybody recognizes on Monday that ammonia is a weak base. And we should know how ammonia behaves in water. So when we look at ammonia or any weak base, it's ripping hydrogens off of the water, okay, to form the conjugate acid and hydroxide. Okay, so ammonia is one of the most popular weak bases here. All right, number 5. Which of the following is true regarding calcium and magnesium? Number 1, calcium has 2 valence electrons in its outer shell. Well, when we look at the periodic table, calcium is in group 2, so absolutely it has 2 valence electrons, so that's a true statement. Number 2, the valence electrons of calcium in a principal energy level N equals 4. Calcium is in the 4th row, and yes, it is in the 4s orbital, so that also is true. Number 3, calcium and magnesium both are diamagnetic, either neutral or when an ion. That is very false. The only time that these are diamagnetic is when they're an ion. Now, however, oh wait, I'm sorry. Let me look at this. I take that back. Diamagnetic means that all the electrons are paired. So magnesium and calcium are diamagnetic. I take that back. Yes, they are. So the calcium and magnesium are diamagnetic, either neutral or when an ion. I was thinking of whoever was to the left of calcium. I apologize for that. Potassium. So actually all 3 of these are correct. So letter E. Number 6. At standard temperature and pressure, or STP, what is the maximum number of liters that oxygen gas that can react with hydrogen gas to form 16 liters of water? First thing that we have to do, this is a stoichiometry problem, so we have to write out the problem, or write out the balanced equation. So we have maximum numbers of liters of oxygen reacting with hydrogen to form water. And again, when we balance these out, let's write down what we know. So at standard temperature and pressure, what is the maximum number of liters, question mark liters, of oxygen gas that can react with hydrogen gas to form 16 liters of water? Now, water is also a gas, so all of these conditions are at STP. So we always start with, first of all, write a balanced equation. Step 2, change what was given into moles. So we need to take our 16 liters and convert that to moles. We are at STP. Be sure you know this. At STP, 1 mole of any gas, 22.4 liters. Gotta know that. Alright, so since we're going from water, we're going to use the mole ratio. So we have 2 moles of water, and we are looking for oxygen, which only has a coefficient of 1. And then it wants to know the volume, so we're going to put 1 mole of oxygen on the bottom. And again, at STP, 22.4 liters. Okay, so we can cancel out anything that's alike. 22.4s go away. 16 divided by 2 is 8. Letter B. Okay. And again, this should not be a major concern for any of you. And again, that took about 1.2 minutes. Just use your time wisely. Don't freak out. Number 7. Which of the following is not true regarding the following atoms? Chlorine -1 and argon are isoelectronic. Alright. Chlorine is right here. Argon is right here. So chlorine -1 and argon are isoelectronic. What does isoelectronic mean? It means it has the same electron configuration. Does not mean that it's the same element. It also does not mean it has the same number of protons. It simply means it has the same number of electrons. Alright, B. Cesium is likely to exist in an ionic compound as a cesium +2 ion. Well, since cesium's right here, it only has 1 valence electron. So it will lose 1 electron and it'll be isoelectronic with xenon. This statement is absolutely false. There is no way that cesium can exist as a +2 charge. Now, just because that's our wrong answer, let's make sure that we can prove the other ones. oxygen is likely to exist in an ionic compound as O with a -2 charge. Yes, oxygen often exists as a -2 charge, unless it's a peroxide. Now, if I have something like hydrogen peroxide, which is H2O2, the per means that I have one more oxygen than my regular oxide. So if I just have oxide, then I'm looking at just O2, but the per means that I'm adding one more oxygen and keeping the same charge. So like when we look at chlorate ions, okay, we have 3 oxygens, but if I'm looking at perchlorate, that's ClO4 with a -1 charge, notice that the charges remain the same, except there's one more oxygen. So this is chlorate, this is perchlorate. Alright, letter D. And again, we're just proving that these are true. Helium and neon are unlikely to participate in covalent bonding with other atoms. That is a very, very true statement, because when we look at helium and neon, they don't want anything to do with anyone else. Now, when we get down here at krypton, xenon, and radon, we're getting into some pretty big atoms here. So we are capable of forming some compounds, although they already have their 8 or their octet of electrons. But there's room for more. Don't forget about these d orbitals. They can always place electrons, more electrons, in these d orbitals. So although the s and p orbitals are filled up, there's still room in the n where we have the d orbitals. Okay? Alright, so that's a true statement. Iodine with a -1 charge and bromine as a -1 charge are stable ions in solution. Yeah, we don't have any issue with these types of ions. Okay, they're stable. They're not going to be crazy or anything. So number 7 should be letter B. Alright, number 8. Which of the following regarding ionization energy is true? Ionization energy is the amount of energy to remove the first electron. In other words, it's the amount of energy to make a neutral atom charged. Okay. All right. So the second ionization energy of magnesium should be smaller than the first. Okay. So looking at the second ionization energy for magnesium should be smaller than the first. Boy, I hate to say this, but that is not true. The first ionization energy for magnesium is small, but once you take one of those electrons away, even though magnesium wants to get rid of 2 electrons, the ionization energy to remove that second electron gets just a little bit higher. And the reason why it gets a little bit higher, if you think about, here's the magnesium nucleus, and we have these 2 electrons that are zipping around in that orbital. If I take one of these electrons away, I still have, I believe there's 12 protons. Let me double check. Yeah, there's 12 protons. So I still have 12 protons in here, or I have 12 positive charges. One of these electrons takes off. Now I only have 11 electrons. And these electrons get pushed in pulled in just a little more tightly, because now I have more of a positive influence than an overall negative influence. Now, yes, magnesium wishes to get rid of 2 electrons, but it's just going to take a little bit more energy to remove that second electron than it did to remove that first one. Alright, so A is not true. The first ionization energy of cesium is higher than that of sodium. Okay, so let's find that. So it's saying cesium's higher than sodium. Well, since cesium's way down here, the trend is for ionization energies as we go from left to right along a row. Left to right along a row, the ionization energies increase. They get higher. Because as we fill up those s and p orbitals, the atoms become more and more possessive, because we're starting to fill those outermost s and p orbital electrons, or those orbitals. So as we drop electrons in, it gets harder, but there are 2 little bumps in the road. After we fill up the s orbital, this third electron actually is a little bit easier to remove than the second electron over here. Because what we're doing is we filled up the s orbital, so the atom's a little satisfied. It's happy that that s orbital's filled up. However, if we just have 1 electron in this first p orbital, it's not so worried about that 1 electron. But as we go from the first to the second to the third orbital in these p's, okay, now what happens is it gets higher as we go from B to carbon, carbon to nitrogen. In other words, dropping electrons from here to here to here. Okay, so now we've got one electron in each of the p orbitals. As we go from nitrogen to oxygen, there's a slight drop in ionization energy from the nitrogen to the oxygen. Why do you think that is? Because boron, carbon, and nitrogen, actually when I have one electron in each of those orbitals, it's half full. That's a special stability. However, it's not a special stability rule. So once we place the fourth electron here in the oxygen, now what's trying to happen is it's not going to take as much energy as it does for the nitrogen to have that electron removed. So there's a slight decrease. And then as we go from oxygen to fluorine, now it starts increasing again. So as we go from 2s, 1 to 2, energy increases. As we go from 2s to 2p, a slight decrease. And then as we go from here to here to here, there's a slight increase, and then there's a bump down. So the key here is when looking at these, see if I can scroll this up a bit. So when looking at 2s, 2p, okay, as we drop our first electron in, it's kind of like, okay, there's our amount of energy. Drop the second electron in, now it takes more energy to remove that one. And then as we put our first electron in, the amount of energy drops. So if this is potential energy here, and this is the number of electrons, etc., the energy is going to drop just a little bit. Do realize that it is much harder to remove this electron than this first electron. That's why it's not below. And as I drop my second one in, it kind of goes up a little bit. Okay. And then as I put my third one in, that goes up again a little bit, so the energy is increasing. As I put the fourth one in, there's a slight drop down. Okay, it's a little bit lower than the one right here, okay, but it's still higher than removing that one. And then as we double them up, it goes up again and up again. Boom. Okay, so when dropping electrons in, and again, we say, generally speaking, as we go left or right along the periodic table, left or right along a row, the ionization energy increases. However, because of the orbitals, that represents the S, okay, now that represents 1, 2, 3, 1, 2, 3 of the electrons, boom, 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 and then there's a slight drop down when we fill up our first double, okay, and then it gets higher as we go along. So make sure that you're aware of that trend. I would love to see a question like that, either in question 5 or question 6 on the exam. How likely is that? I don't know. Alright, so that one's not true. Letter C, the atom with the highest first ionization energy is hydrogen. Well, that's definitely wrong. The one with the highest is helium. In other words, nobody is going to take helium's electrons away without a major fight. Okay. Alright. Letter D, the noble gases as a group have the highest ionization energies. I like that. That's a good answer, and that is true. And then letter E, the atom with the lowest ionization energy is helium. I just talked about that one. That is actually the highest. So number 8 should be letter D as in dog. Alright. Number 9. An atom has the following ionization energies. So we're piggybacking again with ionization energies. Says, so ionization, IE1 is the amount of energy to remove the first electron. IE2 is the amount of energy to remove the second electron. IE3 the third and the fourth. Okay? These values are most likely to correspond with which of the following? Here's what we have to look at when we look at a question like this. Where is the big jump? Where is the increase in energy about 4 times more or greater? So as we go from the first one's always easy. Okay? So as we go from the first ionization energy to the second ionization energy, is there a big jump? Is it 4 times more? Well, it's actually only about twice as much. Okay? So 2 electrons are easy to remove at this point. Looking at IE2 to IE3, is that a big jump? Oh yeah. We have something that's a little bit more than 4% or 4 times. So we know that removing that third electron is difficult. So 2 electrons are easy to remove. The third is hard. What that's saying is, as I look at my periodic table, I'm looking at something that's in this group right here. So anything that's in group 2, anything that's in group 2 or the second column is a viable choice. So I can remove 1 electron, 2 electrons. If I try to remove that third one, I'm pulling it from the core. What is the core? If I'm looking at, say, like calcium, okay, if I have calcium, the core electrons are all the electrons in the rows above. Okay, so in the third energy level, the S and P, in the second energy level, the S and P, and the first energy level, the S, the core electrons. Atoms do not like to have their core electrons removed. So the best choice here is our group 2A element, which is calcium. So again, ask yourself, how many are easy? However many are easy, that's the column that it's in. All right. Number 10, which of the following statements is true? Iron is expected to be paramagnetic. All right, so when we look at the chart here, iron is expected to be paramagnetic. So we have 10 d orbitals here, so we have 1, 2, 3, 4, 5, 6. No way. So when we look at, I'm sorry, it is paramagnetic, it's not diamagnetic. So iron is paramagnetic, because paramagnetic means not all the orbitals are doubled up or filled up. Zinc is expected to be diamagnetic. Zinc is at the end of the column. Okay, so when we look at diamagnetic compounds, we're looking at the end of group 2, or at the end of our s orbitals, the end of our d orbitals, the end of our p orbitals, and even the end of our f orbitals. These are for neutral elements. Okay, so zinc is diamagnetic. Number 3, zinc plus 2, which has a ground state electron configuration of 4s0 3d10, would expect it to be paramagnetic. Well, we have a 4s orbital that has no electrons in it. So what that means is the remaining orbitals have doubles, or they're paired up. This would not be true. So only 1 and 2 should be correct. Okay. When this orbital, if this orbital had 1 electron in it, okay, then it would be paramagnetic. But this is a diamagnetic electron configuration. So 10 should be letter C. All right. Number 11, which of the following concerning PCl5 and PCl3 are true? PCl3 has a net dipole moment where PCl5 does not. The only way you're going to be able to figure this out is by drawing the Lewis dot structure. So we have PCl3, and again, phosphorus brings 5 electrons, chlorine brings 7, so this actually has a tetrahedral shape or trigonal pyramidal shape. PCl5 actually is going to have chlorines all the way around it, okay, which means it's a nonpolar compound. So there's our ugly looking structure there. So it says PCl3 has a dipole moment where PCl5 does not. In other words, it's saying that the PCl3 is polar where the PCl5 is not. And I totally agree with that. That is true. Okay. The geometry of PCl3 is trigonal planar. We got a lone pair of electrons here. So that one is not true. Number 3, both PCl3 and PCl5 use higher energy d orbitals for bonding. Well, phosphorus has the capability of bonding in the d orbitals, but it doesn't need to. Okay, so only the PCl5 uses the d orbitals. Okay, that's the key here. Use. Okay, doesn't mean that it has it. Okay, it is using. So here we're not using that. So really, we only have A. All right, number 12. Which of the following oxygen-containing compounds is most ionic? When we talk about most ionic, we want to look at distance apart from each other. Or if we're looking at two that might be like, here I notice I'm looking right at calcium oxide, which is looking like a real good choice here. If I'm comparing calcium oxide where here is calcium and oxygen's here, those have a +2, -2 charge. If I were looking at, say, potassium and fluorine, I hate to say this, but the calcium oxide's going to win, even though the potassium fluoride are farther away. The reason is more of an ionic charge here. There's a higher charge. So hopefully when you get this type of question on the AP exam, they're going to give you a lot of goofy looking things like this. Silicon oxide, aluminum oxide. Yeah, aluminum is a metal, but it's right in the same neighborhood. So if aluminum were over here, I would go with aluminum, but it is too close. So letter B should be the correct answer here. Okay. Number 13. The carbon atoms of acetic acid, also pictured below, exhibit what types of hybridization? So what it's saying is, what is the hybridization on this carbon and the hybridization on this carbon? So we have two different carbons that we need to be focused on. Okay, so here, if I just look at this carbon, okay, my potential is 4. All right, so we have a tetrahedral shape, and what's the hybridization on a tetrahedral? It is sp3. Okay, if I were looking at a linear shape, which I don't have a linear shape anywhere on here, linear is sp. Trigonal planar is sp2. Tetrahedral is right here. If we had a trigonal bipyramidal shape, which we don't anywhere on here, it's a dsp3. And if we have an octahedral shape, then it's d2sp3. Okay. All right, so let's look at the other one here. Here we actually, this is our central atom for the carbon, so really all we have is that. I wonder what I just drew there. Well, we actually have a trigonal planar shape here because we have only 3 possibilities, or potential is 3. So we have sp2 for that one. So we should have just this and this, so 2 and 3. Looks like D. Okay. Alrighty. Which set of quantum numbers is impossible? Do remember what the set of quantum numbers represents. So the first set of quantum numbers is n. N is our energy level. And n starts at 1 and technically could go to infinity, but it doesn't. It's just 1 and up, let's say that. The second set of quantum numbers is L. And what that is that helps us determine what type of orbital we're in. And this goes from n-1 through 0. Okay? Now, L is special because those numbers actually represent something. So a 0 represents an s orbital. A 1 represents a p orbital. 2 represents a d orbital. 3 represents an f orbital. Sometimes I'll even throw a 4 in there, and a 4 represents a g orbital. We don't care about g orbitals. We didn't talk about it, so don't get your panties in a bunch over it. But do realize that this equation is in play. The third column, or third set of values, is m sub L, which represents our orbitals, and it goes from L, or negative L, through 0 through L. Okay? Be aware, how many orbitals can S have? 1 per energy level. P can have 3 orbitals. In other words, if we have 1, then we're going to go for the P, 1, 0, negative 1. Each one of these numbers represents an orbital. If I look at D, it goes 2, 1, 0, negative 1, negative 2. Each one of these represents an orbital or a different orientation for that orbital. Okay? So having said all of that, let's answer the question. So which set of quantum numbers is impossible? Is A possible? 5, 4, 3, 1/2. Absolutely. That one's good. Looking at this one, we have 3, 0, negative 2. That's pretty bad. Why? Well, s orbitals can only have the orientation of 0. Negative 2 falls in a d orbital's orientation. B is the incorrect answer. or I'm sorry, is the correct answer for the impossible. Alright, number 15. Balance the half reaction for an acidic solution. So we have a redox. First thing that we need to do, we have to balance the non-oxygen, non-hydrogen compounds first. So we have 2 bromines over here. That means we need 2 there. Alright, now we need to balance the oxygens by adding water molecules. So I have 2 times 3, which is 6 waters. And be careful, there's a 2 there and the 3. Okay, so now we have the same number of bromine, same number of hydrogen. Now let's balance out, oxygen. Let's balance out the hydrogens. So I have 6 times 2, which is 12 hydrogen. And again, hydrogen ions, not hydrogen gas. We don't have any gas in this. Okay, then we have the same number of atoms on both sides. So now let's balance charges. There are no charges on the right. That's rare in a redox equation. It can happen, but you don't see it very often. Alright, and then over here we have a plus 12 plus a 2 times negative 1. So that actually is a plus 10 charge. So what we need to do is add 10 electrons. Okay, so whatever that should be, 10 on the left side, A. Okay. Number 16. An aqueous potassium nitrate solution is cooled from 75 to 15 degrees. Which statement from the following is true? The molarity of the solution does not change. Ooh. That's one reason why we use molality whenever we're looking at cooling a solution or freezing point, depression, boiling point elevation, because what happens when water gets cool, it gets denser. When water heats up, it actually gets less dense. So the volume's changing. And it's not just for water, it's for any liquid. If it cools down, it becomes thicker or more dense because it's moving toward a solid stage or a state. So the molarity of the solution does not change is absolutely wrong. The molality of the solution decreases. The molality, that's the nice thing about molality. Molality is moles per kilogram. And again, it's moles of solute over kilograms of solvent. So the reason why we use the kilograms is because the mass of that solvent, the mass of that solvent will not change regardless of what the density is. Okay, if we keep our container and we have that solution in there, even as it flexes back and forth, okay, the mass will remain the same. So it will not decrease. The density of the solution does not change. Absolutely it does. The molality of the solution does not change. That is true. And then just to talk about mole fraction of the solute increases. Well, what the mole fraction is however many moles of the substance we have, and that does not take place. The fraction itself, the mole fraction, this number of moles, does not change. So if I'm doing mole fraction of potassium to nitrate, it's still a 1-to-1 ratio. I still have 1 mole of potassium for every 1 mole of nitrate. So the best answer should be letter D. Alright. Number 17. Bond energies. From the table, determine the enthalpy change for the formation of water. So, again, when we talk about this, bond energy or enthalpy, you can calculate enthalpy a couple of ways, and I expect to see a question like this on the 2011 exam. I expect to see either bond energies or a thermodynamics where you're calculating delta H using a calculator to do it. Regardless, here we go. So we have delta H, and again it's the sum of the reactants for bond energy minus the sum of the products. Now that is opposite when we have heat of formation or heat of reaction. On your periodic table, on your equation sheet, this equation's flip-flop, okay? So it does not look like this. So you have to remember bond energy. Alright, so here we go. We have 2 hydrogens. The way we do this is we draw the Lewis structure. So if I have 2 hydrogens, I'm breaking 1 hydrogen-hydrogen bond within each molecule. So now I've got that times 2, okay, which is like 872. Let's just throw that out there. And I'm guesstimating here, and that's what you're going to have to do as well. And then looking at oxygen, we only have one of those, so that's times 1, which is 499. Okay, so if I want to add those puppies up, we got a 1, we got a 7, and we got a 12. So we got 1271 there for the reactants. 1271. I hope that's right. And then we're going to subtract it from the water. Now, when we do water, again, we have this compound. And again, it doesn't take any bonds or any energy to do anything with these lone pairs because they're not hooked up with anybody. So we actually have 2 of these for every molecule, but we actually have 4, so we need to multiply that by 4. So 464 times 4, that's a 6, 5, and a 18. Okay, so we actually have 1856. So I'm going to do 1856 minus 1271, and I know it's going to be a negative value, so my number is going to be negative, so I can automatically eliminate those guys. And then 71, so that's a 5, that's a 8, I'm going to say E right there, and then so we have a 7 there, so yeah, I can't add. My best choice, because I'm an 85, is letter E. And again, be quick, be efficient. Might want to guesstimate on some of these. Hopefully I did the math did it correctly. I'm kind of going fast here, so I apologize if it's really sloppy. Nice thing is, on multiple choice, scribble, write all over those questions. Just don't do it on the bubble sheet. Okay? And yeah, remember, it is reactants minus products. Alrighty. Number 18. Nitrogen forms a number of oxides. Which of the following oxides is 64% nitrogen? Let's remember that nitrogen has a molar mass of 14 grams for each one. Oxygen is around 16. So what we're looking for is more nitrogen than oxygen. So that one's out, because again, we're looking for 64%. That one's out. That's getting almost to 50%. Here it's a little bit below 50%, so by the luck of the draw, there we go. And if you think about it, we have 28 and 16, so that's almost twice as much as that. Not exactly. It's close enough for what we're doing. Okay? Alright. So letter E for that one. Got to be able to do calculations quickly on this. Alright, number 19. All the following may serve as reducing agents except. Now, what does reducing agents do? Or at least something within the reducing agent? It's oxidized. So what that means is the thing must lose electrons and become more positive. So it needs to become more positive in charge. So some of these things can become more positive, some cannot. Magnesium can... Oh, so it's all but. So magnesium can definitely become more positive because we can lose electrons here. Sodium, if we look at sodium plus 1, we only have 1 electron to give away. It's not going to want to give away any core. Sodium plus 1 cannot be oxidized any further. That was easy. Now, just for the sake of argument, let's look at these other ones. Bromine with a negative 1. Absolutely, we can add, or we can lose some electrons, and this would be a neutral bromine. Same thing with the oxygen. If I have oxygen with a negative 2 charge, it can lose an electron, actually lose 2 electrons, and it can become more positive. And then the lead plus 2, now that one may not be so obvious, especially since you're not given the standard reduction potential sheet that has the charges on the back. But I don't think plus 4 is on the back of that either. But you should know that lead could either be plus 2 or plus 4. So that one's probably not as obvious, but by golly, nobody should miss this because we know that sodium can only be a plus 1 charge. So letter B for that one. Alright. Last question. Number 20. Which reactions would occur at the cathode? Now again, what happens at the cathode? And ox, red cat. So at the cathode, that's a side of reduction, which means that it's gaining electrons. Leo says grr. So we're looking for something that gains electrons. That does. That's losing. That's losing. Yay. A. Alright. That actually concludes quiz number 2 for period number 3. I hope these videos are helping, guys. I don't mind spending the time making these things. I know you're probably getting sick and tired of hearing my voice, but I hope that some of this stuff actually sticks and helps you out. If you have any questions, don't hesitate. Email me.